In this video, we take a closer look at the classification of steels, the various steel types, and their uses. Steels can be classified according to various criteria, with a carbon content generally below about 2%, except for certain high chromium alloy steels. If the carbon content is higher, the material is referred to as cast iron. An initial classification of steels can be made based on their main grade. The main grade refers to the purity level of a steel. A steel is considered especially pure when it contains as few undesirable accompanying elements as possible. This is particularly relevant for sulfur and phosphorus content, as these elements typically lead to brittleness in steel. In the early days of steel production, 3 grades were distinguished: basic steels, also called mass steels, quality steels, and stainless steels. The purity increases from basic to quality to stainless steels. The commonly used main steel grades today are defined somewhat differently. They first consider the chemical composition and its classification into non-alloyed, alloyed, and corrosion-resistant steels. Within the non-alloyed and alloyed steels, a further distinction is made based on purity into quality steels and stainless steels. The steels formerly referred to as basic steels achieve the purity level of quality steels without any great effort in today's manufacturing processes. Therefore, the term basic steels is no longer used in current standards. These steels are now classified as non-alloyed quality steels. For stainless steels, the maximum allowable limits for sulfur and phosphorus are 0.025%. Let us now take a closer look at non-alloyed steels. A steel is generally considered non-alloyed if no alloying element exceeds a certain threshold value. The table provides example thresholds for some alloying elements, which must not be exceeded. Non-alloyed quality steels are steels with basic service properties used for general standard applications. Heat treatment is not common for these steels, but can be applied to certain types. An example is general structural steel like S235Jr, which is typically used in a rolled condition without heat treatment. In contrast, the non-alloyed heat-treatable steel C45 can indeed be used for quenching and tempering. The table lists some non-alloyed quality steels that can be used for a wide range of applications. The specific applications will be discussed in more detail later. The designation non-alloyed quality steel does not imply any particular usage, but simply refers to its basic chemical composition and purity regarding unwanted accompanying elements, and the resulting consistency in properties. The free-cutting steel 11SMN30, and in fact, nearly all free-cutting steels are considered non-alloyed quality steels. The term non-alloyed may initially seem misleading, as additives like sulfur and manganese are directly stated in the steel designation, which might suggest these are alloying elements and thus the steel is alloyed. However, according to standards, elements such as sulfur, phosphorus, and nitrogen are generally considered undesirable accompanying elements, not alloying elements. An exception is made for free-cutting steels, where brittleness caused by sulfur is deliberately desired. Therefore, added sulfur is not considered an alloying element by standard definitions. Moreover, while manganese is mentioned in the steel name, its content is not specified and is kept below the threshold at which the steel would be considered alloyed. The same applies to lead, which is often added to free-cutting steels in quantities below the threshold. Thus, free-cutting steels are generally classified as non-alloyed quality steels according to standards. Let us now turn to non-alloyed stainless steels. In contrast to non-alloyed quality steels, these stainless variants exhibit a higher degree of purity. As a result, the variability in their properties is lower due to narrower permissible limits, which is advantageous for heat treatments like hardening or tempering, where consistent properties and uniform quality are essential. Therefore, heat treatment is common for non-alloyed stainless steels. However, due to the higher manufacturing requirements, stainless steels are generally more expensive than quality steels. A typical non-alloyed stainless steel is, for example, the non-alloyed tempered steel C45E, which offers high wear resistance and is therefore used as a tool steel. At this point, a common misconception must be addressed. The term stainless steel is not automatically synonymous with corrosion-resistant steel. Although all corrosion-resistant steels are made from stainless steel due to the more expensive addition of alloying elements, this does not mean that all stainless steels are corrosion-resistant. The term stainless refers solely to the purity of the steel, not to its corrosion resistance. For example, the unalloyed tempered steel C45E mentioned earlier is a stainless steel in terms of purity, but it would begin to rust in the presence of moisture because it lacks corrosion-resistant alloying elements such as chromium and nickel. Now let's turn to alloyed steels. A steel is considered alloyed as soon as an alloying element exceeds the threshold value specified in the reference table. By intentionally exceeding one or more of these thresholds, desired properties such as strength, machinability, or weldability can be specifically enhanced. Alloyed quality steels, however, due to their relatively low degree of purity and the resulting variability in properties, are generally not intended for heat treatment such as hardening or tempering. In contrast, higher-grade steels, such as stainless steels, are used when heat treatment is required, which is expensive anyway. The third group alongside unalloyed and alloyed steels are corrosion-resistant steels. These form a separate group and are not subdivided into quality or stainless categories. They contain special alloying elements such as chromium and nickel, which provide exceptional corrosion resistance. To achieve corrosion resistance against rust, a chromium content of at least 10.5% is required. Chromium forms a passive layer on the surface that prevents rust formation. Additionally, corrosion-resistant steels often contain other alloying elements such as nickel, molybdenum, titanium, or manganese, which can further optimize properties like strength, toughness, or corrosion resistance against chlorine-containing substances. Corrosion-resistant steels are therefore often referred to as chromium-nickel steels. The term corrosion-resistant steel is used not only for steels that are truly corrosion-resistant, but also for heat-resistant and high-temperature-resistant steels. An example of a heat-resistant steel is the highly alloyed scale-resistant steel X15 chromium-nickel silicon 2521. Scale-resistant steels are heat-resistant steels characterized by high resistance to scale formation. Scale is an oxide layer that forms on steel surfaces at high temperatures and can weaken or visually impair the material. These steels contain specific alloying elements such as silicon, which form a protective oxide layer that doesn't flake off and shields the steel from further corrosion. The steel types described so far primarily provide information about the chemical composition, particularly the degree of purity concerning undesirable accompanying elements in the iron, as well as whether specific alloying elements have been deliberately added. However, the steel grade alone does not indicate the specific application of a steel. For this reason, steels are often also classified according to their intended use. These usage-based classifications will be discussed in more detail in the following. The steel types most commonly used in classic mechanical engineering are the so-called structural steels. These non-alloyed steels are not assigned a specific application purpose by the manufacturer. Sheets, profiles, or bars are often made from simple structural steels. The most widely used structural steel for basic steel constructions is steel S235, which has a yield strength of 235 newtons per square millimeter. For components subjected to higher loads in mechanical engineering, such as shafts, bolts, or axles, the structural steel S275 is also used. For even higher strengths, as required in high-rise construction for crane structures, structural steel S355 is used, which offers a yield strength of 355 newtons per square millimeter. The higher strength of S355 compared to S235 is achieved through the addition of manganese and a finer grain structure. However, the manufacturing process of S355 is more complex, making the steel about 10 to 20% more expensive than S235. These structural steels are easily weldable due to their relatively low carbon content. Additionally, they contain few brittle carbon constituents, giving them excellent toughness, which makes them particularly suitable for forming. The carbon content of these structural steels usually does not exceed 0.22%. However, as the microstructure is relatively soft due to the low carbon content, these structural steels mentioned are not suitable for components subject to wear, such as rails, slides, or gear wheels. For these applications, a higher carbon content is needed to make the steel harder and more wear-resistant. These non-alloyed structural steels are often referred to as engineering steels and are designated with the prefix letter E. Examples include steels E295, E335, and E360. Due to the harder microstructure components, these engineering steels have significantly lower formability and are therefore generally not suitable for forming. At high temperatures and with rapid, uncontrolled cooling, as can occur during welding, the relatively high carbon content of these engineering steels can lead to brittleness. Therefore, compared to structural steels for construction, engineering steels are not suitable for welding. In many applications, components must be weldable and also withstand high loads. Simple structural steels for construction are indeed weldable, but their strength is limited. Increasing the carbon content to boost strength, as done in engineering steels, would again reduce weldability. To keep the carbon content as low as possible for good weldability while still achieving high strength and toughness in the microstructure, so-called weldable fine-grained structural steels are often used. A fine-grained microstructure with many grains and grain boundaries particularly hinders microscopic deformation through so-called dislocations. Therefore, even at low carbon content, a fine-grained microstructure provides high strength and toughness along with good weldability. The grain sizes in the microstructure of fine-grained structural steels are approximately 20 micrometers in diameter. Weldable fine-grained structural steels can be either non-alloyed quality steels or alloyed stainless steels, such as steels S460M or S460N. These are characterized by high strength, with a yield strength of 460 newtons per square millimeter, along with good weldability. Due to the relatively complex manufacturing process involving grain refinement with additives such as niobium, vanadium, or titanium, these steels are more expensive than standard structural steels. Let's now turn to the previously mentioned free-cutting steels. In machining processes, long continuous or stringy chips must generally be avoided, as they can wrap around the rotating workpiece, especially during turning, and cause damage to the component or the machine. This is particularly disadvantageous in mass production on automatic lathes, where downtime may be required to remove tangled chips. The tougher and softer a steel is, especially those with low carbon content, the higher the risk of producing long stringy chips. Therefore, steels were developed that, despite a low carbon content, tend to produce short-breaking chips. Sulfur has proven particularly effective for this purpose, especially in combination with manganese or lead. These elements form low-melting iron manganese sulfides in the microstructure, which promote chip breaking and result in short, fragmented chips. Steel 11 SMNPB30 is a typical non-alloyed quality steel especially suited for machining on automatic lathes, hence the name free-cutting steel. As mentioned earlier, sulfur is not considered an alloying element, and the concentrations of manganese and lead are below the thresholds that would classify the steel as alloyed. While the sulfur compounds in free-cutting steels improve chip breaking, they inevitably increase brittleness and reduce toughness. Therefore, free-cutting steels are generally not suitable for highly stressed components and are also not weldable. Weather-resistant steels, also known as Corrosion steels, are special alloyed steel types that are significantly less susceptible to corrosion than conventional structural steels. Unlike regular steels, they form a dense, firmly adhering rust layer on their surface when exposed to moisture. This so-called patina protects the steel from further corrosion and eliminates the need for additional coatings. In other words, weathering steels do rust, but typically do not rust through like standard structural steels would. Due to their durability, low maintenance, and aesthetic appearance, weather-resistant steels are often used in bridge construction, facades, and artistic structures. They are also popular for private applications such as planter boxes or garden borders due to their rustic look. Typical alloying elements in weathering steels include copper, chromium, nickel, and phosphorus. These elements give the steel its characteristic rust-brown color and self-protecting properties. Compared to much more expensive corrosion-resistant steels, these elements are added only in small amounts. Copper, in particular, is used as a substitute for the more expensive chromium. An example of a weathering steel is the structural steel S235 J2W. The letter W in the designation indicates that the steel is weather-resistant. Another group of steels is known as cold-rolled flat steel products. These are sheet metals that are especially well suited for forming processes such as bending or deep drawing. Their excellent formability is achieved through a very low carbon content. The elongation at break is sometimes over 40%, meaning that these sheets can be stretched to 1.4 times their original length before breaking. This high ductility is essential in forming technology. Cold-rolled flat steel products are used, for example, for car body parts in the automotive industry or as interior panels in household appliances such as refrigerators or washing machines. Due to the lack of strength-enhancing effects from carbon, the strength values of these flat products often remain below 200 newtons per square millimeter. These products, also known as thin sheet metal, are therefore not suitable for heavily stressed components. And the standard designation, cold-rolled flat steel products, begin with the letter combination DC, followed by a number from 01 to 06. The higher the number, the better the formability. This is followed by a dash and an indication of the surface type, uppercase letter, and surface finish, lowercase letter. A denotes a standard surface with typical rolling marks, suitable for general applications. B indicates an improved surface with fewer defects, ideal for applications with higher visual requirements. This is relevant because many cold-rolled flat steel products are painted or otherwise surface-treated for optical reasons. Therefore, the surface finish is indicated with a lowercase letter in the steel designation, B for particularly smooth, G for normally smooth, M for matte, and R for rough surfaces. In addition to structural steels, designated with the letter S, engineering steels, designated with E, and cold-rolled flat steel products, designated with D, there are other steels classified according to their suitability for specific applications. These steels begin with their own identifying letter and are designed to meet unique performance requirements for each use case. Examples include steels for pressure vessel construction, pipeline steels, reinforcing steels, pre-stressing steels, and rail steels. Each of these steel types is engineered to possess specific properties necessary for its intended use. For example, steels for pressure vessels must offer high strength and good weldability to withstand extreme pressures and temperatures. Pipeline steels require high corrosion resistance and pressure strength to safely transport liquids or gases. Reinforcing steel is used to enhance the tensile strength of reinforced concrete structures, improving the load-bearing capacity of the concrete. Pre-stressing steels are high-strength steels used in pre-stressed concrete construction to absorb tensile forces. Rail steels must be highly wear-resistant and tough to endure the stresses of rail traffic. As the suitability of these steels is immediately apparent from their designation, we will not go into more detail about these steels and their chemical composition here. The steels presented so far are generally not suitable for specialized heat treatments. The following steels, however, are specifically designed for or require such treatments. A special heat treatment used to increase strength is quenching and tempering. For this process, the steel must meet certain requirements in its initial state, including a balanced combination of strength and toughness. During quenching and tempering, the steel is first heated, then rapidly cooled, and subsequently reheated at relatively high temperatures. This increases strength while maintaining high toughness, even at low temperatures where standard structural steels would tend to become brittle. Steels suitable for this process are called quenched and tempered steels. They can be non-alloyed or alloyed, and may be either quality steels or stainless steels. One example is the non-alloyed quenched and tempered steel C45, which is often used for moderately loaded components such as bolts or axles. The illustrated stress-strain diagram compares the normal annealed condition with the quenched and tempered condition, clearly showing the significantly higher strength after heat treatment. For more heavily stressed components such as shafts, worms, or gears, the quenched and tempered steel 42 CRMO4 is typically used instead of C45. In the quenched and tempered condition, steels are indeed very tough and strong, but not particularly wear-resistant. However, in some applications, a wear-resistant surface combined with high core toughness is precisely what's required. A typical example is gears, where the tooth flanks at the contact points must be extremely hard and wear-resistant, while the gear body itself needs to remain tough and allow for slight deformation under high loads to prevent breakage. This presents a challenge. High toughness requires a low content of brittle carbon. On the other hand, high surface hardness demands a high carbon content. To resolve this contradiction, steels that are suitable for a specific heat treatment, called case hardening, are used. These steels, referred to as case-hardened steels, have a very low carbon content, less than 0.2%, and are, in their untreated state, very tough. In the case hardening process, the steel is exposed to a carbon-rich atmosphere at high temperatures. During the process, carbon diffuses into the surface layers. Once the carbon content in these outer areas increases to a hardenable level, around 0.8%, the steel is quenched in water. This creates a very hard wear-resistant surface layer, while the core remains tough. Typical components that are case-hardened include transmission shafts, crankshafts, gears, worms, or bearing seats. Example steels for this application include C15 or 17 CRNIMO6. Another surface hardening method besides case hardening is nitriding. In this process, the steel surface is hardened on a microscopic level by introducing nitrogen, which results in exceptional wear resistance, corrosion resistance, and high fatigue strength. To enable the formation of hard nitrides on the steel surface, specific alloying elements must be present. These include additions such as chromium, molybdenum, vanadium, nickel, or aluminum. Steels that are specially alloyed for nitriding are referred to as nitriding steels. A typical example is the alloyed steel 31 CRMO12, which is used, for instance, for dynamically loaded crankshafts. In contrast to other strength or hardness-enhancing heat treatments such as case hardening or quenching and tempering, nitriding does not require quenching, since the increase in hardness and strength is not based on a transformation of the iron crystal structure. As a result, there is no distortion of the component, and dimensional and shape accuracy remain very high. Therefore, nitride parts generally do not require post-processing after treatment. The steels presented so far are primarily used to manufacture components for general applications. However, producing these components requires tools, which themselves are made from steel. These so-called tool steels must withstand extreme forces in some cases. Think of the cutting edge of a file, the punch of a stamping machine, or the blades of a die. Cold working steels are a group of stainless steels specifically developed for tools that are exposed to temperatures of up to 250 degrees Celsius. In most cases, the temperature should not permanently exceed 200 degrees Celsius. These tool steels must have high tensile strength and hardness to endure the mechanical stresses involved in punching, cutting, or bending workpieces. There are non-alloyed cold working steels like C125U, which is used, for example, for embossing tools. The letter U indicates suitability as a tool steel. There are also specially alloyed steels such as X153 CRMOV12, which is used, for instance, for shearing tools in sheet metal processing. In their untreated state, cold working steels generally do not have sufficient hardness to meet tool steel requirements. Therefore, they undergo a special heat treatment by hardening to achieve a wear-resistant surface. High-alloy tool steels can be hardened through their entire cross-section. In contrast to cold working steels, hot working steels are used where high temperatures, thermal shock resistance, and wear resistance are required. These steels are designed to maintain their dimensional stability and strength even at elevated temperatures. Typical applications include casting molds, die casting tools, or forging dies, where temperatures can reach up to 500 degrees Celsius. At even higher temperatures, the tools must be additionally cooled. To achieve high heat resistance, carbide-forming alloying elements such as chromium, molybdenum, or vanadium are necessary. Like cold working steels, hot working steels are heat-treated through hardening and tempering to reach the required hardness. The desired hardness is defined using special tempering diagrams. A typical hot working steel is the highly alloyed X38 CRMOV5-3, which is used for highly stressed forging dies. Another group of tool steels is the so-called high-speed steels. These are highly alloyed steels developed specifically for machining processes involving high cutting speeds and high temperatures, such as turning, drilling, or milling. The main alloying elements in high-speed steels are tungsten, molybdenum, vanadium, and cobalt. In abbreviated designations, these steels are identified by the letters HS, followed by the respective percentages of the alloying elements in the order: tungsten, molybdenum, vanadium, and cobalt. For example, the high-speed steel HS6-5-2-5 contains 6% tungsten, 5% molybdenum, 2% vanadium, and 5% cobalt. It also includes about 4% chromium. This HS steel is used, for instance, in the manufacture of thread taps. To achieve the required hardness and wear resistance, high-speed steels undergo a hardening process in which the steel is heated to over 1,200 degrees Celsius and then rapidly quenched in a salt bath. A subsequent tempering step at around 550 degrees Celsius provides the final mechanical properties. Compared to cold or hot working tool steels, HSS cutting tools allow for cutting speeds that are about 3 times higher. Another group of steels is known as spring steels. These are characterized by their high elasticity, toughness, and fatigue strength. They are primarily used in applications where materials must return to their original shape after being deformed, for example, in springs, clips, or latches. Spring steels can be non-alloyed or alloyed. Non-alloyed spring steels like C75 are particularly suitable for applications at room temperature. Alloyed versions, such as 51 CRV4, maintain their performance even under higher temperatures and dynamic loads. A key part of manufacturing spring steel components is heat treatment. These parts are often first soft annealed and then quenched and tempered to achieve high tensile strength and toughness. Typical tensile strengths range between 1200 and over 2000 newtons per square millimeter, which is around 4 times higher than that of standard structural steels. Heat treatment also ensures that the steel retains its strength under repeated loading. However, not all spring steels require heat treatment. Some achieve the required strength through the manufacturing process itself, for instance via cold rolling, which induces strain hardening. Let's move on to the group of corrosion-resistant stainless steels, which we explained in more detail at the beginning. These corrosion-resistant steels can be subdivided according to their microstructure into ferritic, martensitic, and austenitic steels. Ferritic steels are characterized by a predominantly ferritic microstructure. This is a nearly carbon-free, body-centered cubic lattice structure known as ferrite, which gives the steel its name. Ferritic steels contain very little carbon, usually less than 0.1%. However, a high chromium content of over 10.5% up to 30% is required for corrosion resistance. On the other hand, ferritic steels contain almost no expensive nickel, which makes these corrosion-resistant steels relatively cost-effective. Typical ferritic steels include X6CR17 or X2CRT12, which contain no significant amounts of nickel. Due to the absence of nickel, their toughness at low temperatures is limited. In particularly cold environments, ferritic steels therefore often tend to become brittle and are not particularly suitable for forming. Additionally, these steels are not especially well suited for welding, as carbide precipitation increases significantly at temperatures around 600 degrees Celsius. When chromium carbide settles at the grain boundaries, it becomes depleted in those areas of the steel's microstructure. The chromium-depleted zones at the grain boundaries become more susceptible to corrosion. This can lead to the steel being attacked along the grain boundaries, potentially resulting in intergranular corrosion failure. For this reason, titanium or niobium is often added for stabilization, as they preferentially form stable carbides, allowing the protective chromium to remain in the microstructure. Ferritic steels are not hardenable due to their low carbon content and the absence of a lattice transformation caused by the high chromium content. However, the ferritic microstructure makes the steel magnetic, in contrast to the austenitic steels, which will be discussed in more detail later. If the carbon content of corrosion-resistant chromium steels is increased to above 0.2%, the lattice transformation necessary for hardening reoccurs in the steel. After hardening, a very hard martensitic microstructure is formed. Such steels are referred to as martensitic steels, where resistance can be further enhanced through the addition of the alloying element vanadium. Molybdenum also improves the corrosion resistance. A typical martensitic steel is the highly alloyed steel X50CRMOV15, which is frequently used in knife tools. The also corrosion-resistant austenitic steels have a face-centered cubic crystal structure. This face-centered cubic microstructure is also referred to as austenite, which gives these steels their name. Unlike the ferrite structure, however, the austenite structure is non-magnetic. Therefore, it is possible to quickly determine whether a steel is ferritic or austenitic using a magnet. The most well-known austenitic steel grades are X5CrNi1810 and X6CrNit1810. Based on the chemical composition, it is evident that austenitic steels contain significantly more expensive nickel, making them more costly than ferritic steels. The high nickel content ensures that the more easily formable face-centered cubic austenite structure remains stable even at room temperature. Therefore, austenitic steels are more formable than ferritic steels and remain relatively tough at low temperatures without becoming brittle. Austenitic steels are also weldable, but they are not hardenable. Due to their relatively high chromium content, these steels also exhibit excellent corrosion resistance. However, the strength of austenitic steels is lower than that of ferritic steels. A further development of these corrosion-resistant steels are the steels X5CrNIMO1712-2 and X6CrNIMOT1712-2. As the name suggests, these austenitic steels also contain molybdenum. This makes the steels not only resistant to water, but also particularly resistant to chloride-containing media, such as seawater or chlorinated water in swimming pools. As a result, these steels are often used in such environments. Ideally, the high strength of ferritic steels should be combined with the exceptional corrosion resistance of austenitic steels. This is achieved with so-called duplex steels. As the name suggests, duplex steels are a combination of ferritic and austenitic steels. Duplex steels are characterized by a two-phase microstructure consisting of austenite and ferrite. This combination brings together the high corrosion resistance of austenitic steels with the high strength and stress corrosion cracking resistance of ferritic steels. Typical examples, such as the material X2CrNIMON2253, contain about 22% chromium, 5% nickel, 3% molybdenum, as well as additional elements like nitrogen, which further improve the mechanical and chemical properties. A particular advantage of duplex steel is its resistance to chloride-induced corrosion, especially against pitting, crevice corrosion, and stress corrosion cracking. It is therefore highly suitable for applications in aggressive environments, such as in offshore technology, seawater plants, the chemical industry, or bridge construction. In addition, the strength of duplex steel is approximately twice as high as that of conventional austenitic steels, which often allows for weight or material savings. However, processing, especially welding, is more challenging than with conventional corrosion-resistant steels.